work at TIFR. I'm a theoretical physicist, unlike Professor Datar, who's an experimentalist. So I work with pen, paper, and a computer. He works with real stuff. It's a much harder job, what he does. It's a little change of, let's say, direction. This is INO week. We'll be discussing about the India-based neutrino observatory. You've heard Professor Datar's talk, a beautiful overview of about neutrinos and about what INO will do. You will also hear a few other talks throughout this week if you're here. My talk is not about neutrinos. It is about dark matter. If you already know a little bit about dark matter, that's lovely. Otherwise, don't worry, I'll tell you all about it. But it's not that dark matter is like totally different from neutrinos. You'll see that there are strong similarities, so which is the reason why this talk still appears within the INO week, and I'll tell you what the similarities are and what the differences are. Okay, so let's start. How many of you recognize this picture? Is there anyone who does not recognize this picture? Just raise your hand. It's fine. Okay, so everyone, oh, you don't? No? Okay, okay. So for those of you who do recognize this, can anyone say what this is? This is Mumbai, right? Okay, so this is Mumbai. What is this? This is Pune. Okay? How many of you can say what this is? Hyderabad? Okay, so now slightly harder question. What is this?
Oil rigs.
Correct. So these are the oil rigs, Bombay High and so on. Very nice. So this is, of course, a satellite picture of the Earth, the region around Mumbai. This is Mumbai. This is Pune. This is Hyderabad. Bombay High, so on and so forth. Gujarat. This is look. Now, if I ask you, what is this dark stuff here? What is your answer? This is where there's less electricity. This is where fewer people live. So there are no, street lights. So that's why, it doesn't look brightly lit. Now, what is this dark stuff? This is Arabian Sea. There are no people there. They have not turned on the lights. So that's why it looks dark. So it's very obvious to us. Our intuitive understanding, we look at a picture like this, there's some stuff that we can't see. We don't immediately say that it's nothing, that there's nothing out there. We never say that, right? But okay, let's see if the same thing is true now. What is this picture? It's a night sky, exactly. This is a picture that I took actually at a national park a couple of years ago. So these are some stars. Now this is a picture taken with, let's say, about 1 second exposure. So you don't see very much. If you turned off the lights, you would see a little bit more. Can we turn off the lights maybe a little bit? There's no one here. Fine. All right, never mind. So now, this is the same picture. I've not changed anything. Actually, it's the same picture. In the previous one, I had artificially made it darker. Now, this is the picture as I took it. Okay. Now, do you recognize this picture, some of you? So this is the Milky Way. I don't know if you can see that there's this outline of trees here. Yeah. Can you see that? Very good. And so this is the Sagittarius arm of the Milky Way, and these are the stars. Now, if I point to you and let's say, okay, very good. Thank you. Thank you. Let me show you the previous picture, just for contrast. So this is what the night sky actually looks like in Mumbai, right? But if you go to one of these night sky observation sites near Mumbai even, and if you're a bit lucky with the clouds, you can see this sort of a picture. I must admit, this is not a picture taken from Mumbai. So this is a picture taken from a place which is much darker than Mumbai. It's a class 4 dark site where you can basically see about 4 times as many stars. So this is the Milky Way. Now if I point at some dark spot in this picture, let's say here, okay, and I ask you what is there, what is your answer? Like what's there in that dark region of the sky?
Others.
I'm sorry?
Other stars.
Other stars? I'm sorry?
whose light we can't see. It's maybe too dilute for the eye camera.
Good. So that's one possibility. Okay, so let's do that. So let's say so this is me, an amateur taking night sky photographs. Let's show you a picture of someone who's a professional. And now this is something that's really, really good. And now I ask what's going on here. So let's say that this guy is super good. All stars that could exist have been seen here, but there's still some dark stuff here. Okay, this is just haze from the Earth. But let's say here, this dark sky here. Is there nothing there, or is there something there? There's something there. What is there? Okay, so the point is that if you look at even deeper pictures of the sky, so now this is a composite of two pictures. So both of these pictures are taken using the Hubble Space Telescope. So this is the picture of a pinwheel galaxy, and then this has been superimposed on the background, on a much wider field background of the sky, taken again using the Hubble Space Telescope. And now you can believe me when I say that all the dots that you see in the background are not stars. These are other galaxies, and they've all been seen. So there is no star that's hiding here. And there's this dark area here. Is that empty? I'm sorry? Yes, no, maybe?
Things that we have not yet detected.
Dust, yeah, maybe not. Good. I mean, so these are all. So, but okay. So as you see, because I primed you with that picture of Mumbai and the sea and the dark regions, you are now primed. Your intuition is already along the correct direction. You see dark parts of the sky. You're not saying that it's empty, that it's a vacuum. But if I'd asked you the same question, before showing you that Mumbai picture and ask you, the dark part of the sky, you don't see any stars there or any galaxy there. What is it? You would have said empty space, right? So that's the standard answer. So the whole point of my talk is that the universe is not full of empty space. Most of the universe is full of something else. It's dark, we don't see it, but it's there. And we have very good experimental evidence that it's there. A fraction of that dark stuff is something called dark matter. Okay? But there's something else which is called dark energy, which I won't tell you a lot about, but a little bit. Okay? So the rest of the talk is all about telling you how we know that there is this stuff called dark matter. So I'll tell you 5 different ways in which we can convince ourselves that there is dark matter. And then if there's time, I'll tell you how we will know what this dark matter actually is. Okay? Clear so far? All right. All right. So actually, if we do computer simulations of what the universe looks like on the largest scales. So the picture that I had shown you just before, let's go back once. So this is a galaxy. So a galaxy like ours, like the Milky Way. This is about 10 kiloparsecs in size, in diameter. A parsec is 3 light years, 3.26 light years. 10 kiloparsecs, therefore, means 30 light years. Okay? So this object is about 30 light years across. I'm sorry, 30,000 light years. You're right, thanks. So 30,000 light years across. Now, if I simulate, so on the computer I make a model of the universe, but on a much larger scale. So this is 100 million light years. So 30,000 light years was about this much. Now this is 100 million light years. So actually that would fit in a little box over here. Okay, so this is a much bigger box. So each point here, each yellow point that you see here, is not even a galaxy. It's like a cluster of galaxies. Okay? And I don't know if you can see, but these clusters of galaxies are embedded in a hazy cloud that I have colored gray or white. Can you guys see that? So this is, of course, all synthetic, that it's all made on a computer. This is not real stuff. this is not something that you can see very easily with a telescope because you need this kind of wide angle. But just to give you an impression of what it really looks like, all galaxies and clusters of galaxies are embedded in this cloud of this hazy stuff, which is called dark matter. And I'll tell you how we know that. But I first want to give you a visual idea of what it looks like. This is what the universe looks like on the largest scale. Okay, we live in some place like this. So we are part of this big, Virgo supercluster, and Milky Way is just one galaxy which is part of this cluster, and the Sun is one of a billion such stars. Then the Earth is just one of 8 planets around that Sun. Okay. So this is how the universe looks like at basically the largest scales. This white hazy stuff, this is dark matter. But around a galaxy, like ours, it's a big galaxy. Around a galaxy, so this is, let's say, the visible part of the galaxy, which I was showing you is this, let's say, 30,000 light years or whatever. So this is 100,000 light years. It's a little bit larger galaxy. But there is this big halo of dark matter around each galaxy as well. Okay? So the way to think about dark matter is this, that each of the galaxies sits in a hazy halo of dark matter, about 10 times its size. And then all of these dark matter halos, kind of fit together in this big network, or if you want to think of it in terms of a big cosmic web, within which these galaxies are studded like jewels. So that's the picture of the universe. Now I'll tell you how we know it. Okay? So let's start. So just for fun, I don't know how many of you like Calvin and Hobbes. This is one of my favorite comic strips. I've been, as a child, this used to come in the Sunday magazine that came with the newspaper that we used to get. If you haven't read this comic strip, you should, because it's one of the most original things that you can read. So this guy, his father is super funny because he tries to teach him all sorts of interesting stuff, sometimes wrong things even. And this guy is super smart. And so every once in a while he makes comments that you come back 15 years later when you're not reading it as a kid, and you realize how smart the guy is. When he says that scientists come up with all sorts of very interesting things and then they give them dull, unimaginative names like dark matter. It's the least interesting name that you could have given to this thing, but anyway. And I'll show you how we've given an even less interesting name to yet another thing called dark energy. But that's my apology on behalf of physicists that we are not very creative when it comes to giving names. But let's see, how do we know that there is dark matter? So the main idea that we will use to establish that we know that there is something called dark matter is this trick that we learn in school, that you can use the motion of objects to measure the mass of the object or the object that's causing the motion. So if that's not already clear, it will become clear in like 2 seconds. This is elementary stuff. Okay, so this is Mr. Newton standing on our Earth, and he gave us this second law that force is mass times acceleration. Okay, but what force is this? So let's say if I'm talking about dropping my keys, which I have in my pocket. Okay, so here are my keys. All right, so I take my keys about 1.5 meters up from, let's say, the surface of Earth, and the force acting on this thing, that I have to hold onto it so that it does not fall down. Why? Because there is a gravitational force of the Earth that's acting on it. If there was no Earth, if I left it, it would just stay here, right? So I have to hold it back from the Earth, to prevent it from falling. How much force does the Earth apply on this key? Let's say the mass of my keyring is this small m. Let's say the mass of the Earth is this capital M, and I am capital R distance away from the center of Earth here. So this force is g/m by r square, and that is equal to mass times acceleration. Beautiful thing that this small m cancels. So whether I use this keychain or your keychain or something else, an apple or whatever, doesn't matter. This is fine. Now, school level physics, all I have to do is I need to know what is the radius of Earth. I need to know what Newton's constant is. Both of these things are there in textbooks. And what I do is I just drop it. So suppose this, I know the height is about, whatever, 1.5 meters or something. So let's say I write 1 meter. And the time it takes to drop is about half a second. Okay? So good. So if it drops about half a second, if it drops a meter in about half a second, I can measure the mass of Earth. Because I can rearrange my equations in such a way that I can measure the mass of Earth to be 5 times 10 to the 24 kilograms. Okay? So this is an experiment that you can do at home. You can do it here. All you need is a stopwatch and just whatever, a scale to measure the distance. It won't be terribly accurate, but you will be correct to within 10% or so. So maybe this 5 becomes a 6, maybe it becomes a 3, but this 10 to the 24, you'll get that right. So that's brilliant, right? I mean, with a 5-minute experiment that you can do in your backyard with, supplies that you have basically sitting in your house, you can measure the mass of Earth. That's kind of remarkable, right? All right. So this is how you measure mass of some object by looking at the motion of some other object which is affected by the mass of this big object, right? So this is the trick. And now we will use it again and again. So the first application of this trick to discover dark matter is this. So here is a picture of a part of the sky. This is, let's say, longitude and so longitude and latitude on the sky. It's called right ascension and declination. And each of these points is some astrophysical object. They are color-coded. Some of them are red and some of them are blue. They're color-coded by their speeds. Okay, speed on the sky. Now you can see that they're all different, and I have just, it's hard to read this. I'll just tell you that the blue ones are about 1,000 kilometers per second. Blue ones are 10,000 kilometers per second, and the red ones are 1,000 kilometers per second. So the red ones are slower, the blue ones are faster. But the fact is that there is a big difference in these speeds. Now, you have already read this in school that the typical jiggling of molecules in a box depends on temperature, right? So if you heat a box of gas up, the molecules of gas in this box, they start moving faster. The same thing is actually true of galaxies interacting with each other through their gravity. So suppose you have a big box inside which there are lots of galaxies. They're all interacting with each other through gravitational force. If you have lots of mass, each of these galaxies is zipping past many more galaxies, and on average, they are speeding up. Now, of course, if all the galaxies are moving coherently with some speed in one direction, this does not count towards overall mass, because this is not the random speeds. So the part of temperature that you know that comes from velocities is the random part of the velocity. So similarly here, what I really care about is what is the random fraction of the velocity. That is what will tell me what is the overall mass in this box. A good way of estimating the random fraction is to look at not individual velocities, but the differences in velocities. Because if everything is moving in one direction, let's say at some speed v, that if I subtract from each one of them, I can go into some frame where nothing is moving, right? So that would tell me that the thing is actually at zero temperature, there is no mass actually in there. But the fact that there is such differences in velocity tells you that in this little region, there's a lot of mass. So you can estimate how much mass there is using basically the Virial Theorem, if you guys are familiar with it. The idea is that the kinetic energy and the potential energy are related to each other by some overall factor. The kinetic energy you can estimate by just measuring the velocities, and the potential energy is given by g/m by r, as you learn in school. And then you can rearrange this equation to again write down mass in terms of the size of the object, the average velocity dispersion, this is a random part of the velocity, and the Newton's constant. So the same sort of exercise that we did with the key, except that now we apply it in the sky. And doing this, you can measure the mass. So this was done for the first time by Fritz Zwicky. He was a Swiss-American astronomer at Caltech. This is his paper. And he estimated that the mass in some cluster called the Coma cluster was 400 times larger than what was seen. Of course, a large fraction of this mismatch of 400 comes from unseen things. There are galaxies that are just hard to see. But not all of this can be explained simply by including more and more stars and more galaxies. So there is quite a large part of this mismatch that cannot be explained unless you postulate that there is some mass out there that you cannot see. We call that dark matter. In fact, he calls it Dunkelmaterie, that's German for dark matter. Okay, so that's the first one, that the jiggling of galaxies or the whizzing of galaxies in galaxy clusters, using the Virial theorem, I estimate that there is more mass than I can see. The next one is much easier. You know how something orbits another thing. You can calculate how much time it takes and how it depends on the mass of the object at the center. In fact, for various objects in our solar system, this is the distance from the sun. This is the speed, orbital speed of that object, and it follows this Kepler's law. The velocity goes as 1 over square root n. And the proportionality constant is square root capital M, this mass of the sun. But it follows this shape. So what you see is that if all the mass is, at the center, basically all the mass in the solar system is here, the sun is the only massive thing in the solar system, the orbital velocity falls off very rapidly, and things far away don't move very fast. They're going very slow. That's the main point. Now, if I look at our galaxy, okay, so these are two synthetic images again. They have been made to rotate in two possible cases. So one is what you expect. So if all the mass is, inside this region, how it will rotate, and if all the mass is not in this region, but instead there is further mass around it, like how I showed you, like this big halo, how this would rotate. So let's see how this looks. So now you see, what you expect, if all the mass is here, the edges are not moving at all. Whereas if there is mass outside the galaxy which you are not seeing, you can see that the edges are moving. Now these are both simulations. I can go out there in the sky with a big telescope, look at how each galaxy around us is rotating. Right? I just measure the Doppler velocities of each of the stars at the edge of, let's say Andromeda. And I can find out if Andromeda looks more like this or more like this. Turns out Andromeda looks like this, not this. Tells you that there is mass around Andromeda that you are not seeing. And same for every other galaxy. So I've told you two ways so far that we know that there is dark matter. The first was this average velocity of galaxies in a cluster of galaxies. This is the old Zwicky idea. This is called rotation curve of galaxies, because not only can you measure the velocity of rotation here, but throughout as a function of radius, you plot that. So this was done, among others, by Vera Rubin, and this is her data. This is the distance from the center of M31 galaxy, it's Andromeda, and you can see that the velocity is not decreasing. It's kind of flat, right? Whereas this orbital Kepler law would have told you that it goes down as 1 over square root r, okay, as I showed you. So the fact that this does not decrease tells you that there is mass here. See, the galaxy has finished here. The galaxy is, this is the galaxy, it's done. But the velocity is not decreasing, it's continuing on. So there is mass here that's not part of the galaxy, it's dark. That's So she and her advisor, Ken Ford, found this second line of evidence that there is dark matter. Okay? The third one is also something familiar to you. You guys have all heard about Einstein's relativity. Light bends around massive objects. What happens is that suppose there is some distant galaxy which is very bright. Let's say it has some very bright, object called a quasar. Light from that object has to go around other massive objects which are intervening, let's say this quasar and us at Earth. So the light bends around this massive object, and it bends around on both sides, and you see two images of the same star or of the same quasar. Such things have been seen, and then therefore you can measure the mass contained in this object using the amount of this bending. And from that again you can recover that the mass in this galaxy cluster is observed to be less than what is predicted by the amount of bending. So the lensing predicts a certain mass, whereas you can only measure a certain mass by just counting the galaxies. Tells you that there must be more mass. So there's the third line of evidence for dark matter. There's two kinds of lensing, something called strong lensing and weak lensing. When strong lensing happens, there are multiple images. Weak lensing just leads to slight distortion. In both cases, you can measure the mass. So this is an example where you see both strong lensing and weak lensing. So you can see that there are these little streaks here, right? So this is just a star in the background that has been stretched because of this lensing due to the galaxy cluster in the intervening region. Whereas there are certain sources that are multiply lensed. So for example, let's see if I can find for you something that looks like there are two of them, but they're actually the same thing. Let's see. I used to know for sure. Let's see. Yes, you see, there's this red galaxy here, and then there's this red galaxy, exactly the same shape, just a different size, same color. It's very unlikely that you will have two galaxies, exactly the same shape, exactly the same color, just differing in size. What has happened is that there is a lens sitting here. It has created two images. This has been magnified relative to the other one, and these are actually just the same galaxy which is somewhere behind. So most likely what is happening is that this is the real galaxy, and this is the magnified image of that galaxy. So that's strong lensing. So again, from this, you can find out that there's dark matter because you can measure how much mass there should be in order for such things to happen. Okay, so the fourth way that we know that there is dark matter is something called the Big Bang, in particular by looking at the cosmic microwave background. So let me first tell you what the cosmic microwave background is. Okay, so when I'm looking at you, I am looking at you as you were at a time that it took light to get from you to me. So for example, if you are, say, 1 light year away from me, I will see you a year younger than you actually feel, right? Because I see you as you were a year ago. So when we look deep into the sky, into the universe, we look at objects as they were at a time that the light was emitted from them, and it is now reaching me. Okay? So when I look at the sun, I look at an 8-minute-old sun. When I look at a galaxy that is 30,000 light years away, I look at a galaxy that's 30,000 years old. The galaxy might have just disappeared by now. I mean, maybe there's a star which I look at, and the star just became a supernova, and I mean, it's not there anymore. But I see it because I'm looking at it 30,000 years, earlier than it right now is. So in some sense, this is mind-boggling, but okay, this is how it is. So if you look at deep in the universe, not at a star, not at a galaxy, just through some little corner in the sky which looked very dark and there were no sources, eventually I am looking at a part of the universe that was very, very, very old. Right? The further I look, the older it gets. And I can just choose to look at some region which is just extremely old. How old? Well, as old as it takes to make sure that the universe was very hot and dense. So the universe started very small, it expanded and cooled. So if I go far enough, I'm going old enough that the universe was hot and dense, and it was completely ionized. So the protons and the electrons were not forming hydrogen atoms. It was so hot that everything was ripped apart, and the universe was just full of, as a soup of particles, electrons, protons, and neutrons just zipping around. And it's just a soup of charged particles. It's a plasma. Okay? So if I'm looking far enough, I'm looking old enough, I'm looking at hot enough, dense enough, charged plasma. And of course, light from this charged plasma can't really come to me. So what really happens? So I'm looking at this universe. I can keep going until I hit this point at which universe became neutral. Beyond that, the universe is opaque, and light from beyond that cannot come to me. So light can only come to me from this surface where the universe became neutral. This is called the last scattering surface. Okay? And this is what is known as the cosmic microwave background. So the photons that come to us from this time at which universe became neutral is the cosmic microwave background. And it's there in every direction, because you have to go basically the same distance in every direction to get to that same age at which the universe became neutral. Okay? Make sense? Everyone with me so far? All right. So if you look at far enough, you're looking at an old enough, dense enough universe, which is beyond that point opaque. So that's the last scattering surface. Now, that surface is something, let's say with some telescope I can look at that surface, it's part of that surface. Is that surface featureless? No. What's happening is that, imagine beyond that wall, there is this dense plasma. And I can, ping that little plasma, and there will be a little wave that propagates in this plasma. And I could do it at every possible point. So what's happening is that there are all sorts of waves propagating in that plasma beyond that last scattering surface. And these are ripples. Ripples on this plasma, ripples on a cosmic pond. And what do I mean by waves? Waves means that there are density waves. Density increases or decreases a function of, just like how when I speak, the gas molecules vibrate on from my mouth all the way to your eardrums, and this change in density is what leads to a change in pressure, and that's what makes your ears vibrate, and that's what you perceive as sound. The same thing will happen with density waves in this plasma, where the change in densities are related to changes in temperature, right? And changes in temperature are something that I can measure by looking at the energy of the photon that is coming from that surface. So if I look at the temperature at each point on this surface, I am measuring the state of the oscillation, whether you were in a compression or a rarefaction at the point of decoupling on that surface. So I can do that. So let's say what's happening is that on this surface there is gravity that is pulling stuff in, and radiation pressure that's pulling stuff, pushing stuff out, and this makes everything oscillate. And I'm measuring the temperature fluctuations at each of these points, and I ask, how does the temperature fluctuation here compared to the temperature fluctuation there. And let's say these 2 points are separated by some angle. Let's call that 2 degrees. So let's say I take 2 points which are 2 degrees apart, and I ask, are the 2 temperatures the same or different? So there's some way of thinking about it. It's called a power spectrum, and it turns out that as a function of this angle, whether they're very close or very far apart, there is a preferred angle close to about 2 degrees at which you find that these 2 temperatures are very similar to each other. When you make this angle smaller than that, here, it increases and decreases periodically. Whereas if you make this angle larger, it just simply becomes small. So basically, if this temperature is a little bit higher than average, as you go more than 2 degrees away, this temperature becomes unrelated to this. You can't predict. Whereas if they're 2 degrees apart, you can almost always predict that, okay, if you are about a factor of 10 power minus 5 larger, you will be a factor of 10 power minus 5 larger or smaller exactly here too. So at 2 degrees, there is this very strong correlation. So this shape gives us a lot of information about the nature of oscillations in this early universe plasma. Okay, so this is known as the cosmic microwave background power spectrum. And in particular, the different features of this curve tell us about how much matter there was, what fraction of that matter was interacting with photons or not, and so on. So in particular, the height of this peak tells you the total amount of matter. So that is measured, and so you see this curve that is running through is theory. All these points are data. In fact, the data is much better now. This is very old. The height of this peak is very well measured, so you know the total amount you know. The height of the third peak basically depends on dark matter, and because it is measured, I can tell you how much dark matter there has to be in the universe. There is an independent way of measuring dark matter just within this picture, which is the slope of this last part. The tail of this power spectrum, it goes up if there is more dark matter and comes down if there is less dark matter. Again, you can understand these things from the fact that this falling off is happening because photons leak out from potential wells. If there is more dark matter, they leak out less. If they leak out more, if there is less dark matter, they leak out less. And that's what leads to this behavior. Anyway, so you can play with this, and one can just run these calculations. And what's happening here is I'm changing the amount of dark matter from 0.5 to 0.1. And you will see that once I get to 0.3, the picture looks most like the picture that I had shown you. So that tells you that 30% or 25% of the universe is dark matter. Because once you get to about 25, that's when this picture looks most like the real data that we've measured. Okay, so 4 ways of knowing about dark matter. So clusters, rotation curves, lensing, CMB, and now the final one, the cosmic net. So this is an actual map of galaxies around us. So we are here. What is being plotted along the radius is distance from us, essentially. And this is just angle around us. These 2 dark regions are where we have not been able to see, because that is the disk of our galaxy. So we can't look through our galaxy because there's just too much stuff in the way. It just gets in the way of being able to observe other things. But we can look up and down from our galaxy with telescopes, and that's what we see here. And I had shown you this synthetic image of how the universe looks on large scales. So that was a simulation. This is not a simulation. And I think you will agree that they look very similar, like this and that. The scale is a little different, but still. So this is the cosmic net. Now you see that there is some kind of clustering. That, you can see these filaments, you can see these little, clusters of galaxies over here. If you did not have dark matter, you would not see such sharp features. Everything would be just smeared out. Okay? So the fact that we see such features requires us to then postulate that there is dark matter. So there is totally 5 different ways that we know that there is dark matter, and they cover different scales. So let's go about all of that. So this is at the smaller scales, at milliparsec scales. So around the solar system, we have no evidence for dark matter. Okay? But as soon as we go to the galactic scales, about 100 kiloparsecs, we have evidence from rotation curves and velocity dispersions that we need dark matter. Once we go to about a megaparsec scales, there is evidence from lensing that there is dark matter, evidence from galaxy clusters. Once we go to about a gigaparsec, which is basically the size of the universe, 10 times, a factor of 10 smaller than the size of the universe, we have evidence from the CMB and large-scale structure that there is dark matter. Okay? And all of this is telling us what? That there is some mass that we need in order to explain motions of other particles in the universe. Okay? Even the last one where I showed you the cosmic wave, when I say clustering, I mean that the particles should not move too fast. If particles whiz around too fast, then you will not have nicely defined structures. So the fact that you need some mass that is holding galaxies in their place is evidence for dark matter. So similarly for rotation curves, clusters of galaxies, and this dispersion of velocities, lensing, so on and so forth. So all these different lines of evidence for dark matter are essentially the same thing. Fundamentally, it is the fact that we need more mass in order to explain the motions of various things, light, galaxies, what have you. Okay? But we do not know what is this mass consisting of. So we are used to, so if I tell you that I have 1 kilogram of something, you are legitimately allowed to ask me, what is this something? I mean, is it potatoes or is it onions? Right? So, and I mean, if you're a physicist, you'll say, okay, I don't care if it's potatoes or onions, but it's protons and neutrons and electrons. So you're, legitimately allowed to ask me that, okay, you're telling me there's all this mass out there. What is it made of? Are these electrons and protons or neutrons or something else? So this is the interesting question, and I think I have another 5 minutes or so before I wrap up. So let me try to get a little bit into that question, but before that, just 2 slides on dark energy. So the dark energy is something different from dark matter. It's not dark matter. Dark energy is a name given to the phenomena that the universe is expanding at an accelerating rate. So what does it mean that the universe is expanding? So imagine that this is the universe. So you are sitting on this galaxy, the other galaxies around you. You would see that the galaxies around you are receding away from you at some speed. This is Hubble redshift, and that's why I've colored them red. So now if I superimpose one on the other, like this, so you see that this galaxy, each of these galaxies is going away from you. The same thing happens if, let's say, you were not on this galaxy, but rather on that galaxy. This is what you see. You see the other galaxies as red. You don't see your own galaxy as getting redder. If I superimpose, you see that every other galaxy is going away. Believe me, these are the same pictures. All the pictures, they're just shifted. It's a question of reference frames. And so what it means is that every point is going away from every other point. But the question is, at what rate? At a constant rate, or at a rate that is decreasing, or at a rate that is increasing? Turns out that our universe, we have measured how galaxies and stars are going away from us. It requires us to lie on this red curve, which basically requires us to postulate that there is 70% of the universe that is something that leads to this acceleration. This 70% is called dark energy. We know even less about it than we do about dark matter. Okay? So I'll not talk more about this, but dark matter. Let me make a comment about neutrinos. How do we know about neutrinos? Turns out that neutrinos are a bit like dark matter because we can't see them, but they contribute mass. But they're very light, so they whiz around too much. So they lead to smearing of structure. The fact that we understand this CMB curve tells us that we have the correct energy density corresponding to about 3 active neutrinos. But they cannot be all of dark matter in any case because they're too light. They don't give enough mass. And they would have smeared the galaxies too much. So we know from the observation of the CMB and the large scale structure that neutrinos have to be there, but they are not too many of them, and that they're light. This tells you about dark energy. So basically the budget of our known universe looks like this. 70% or basically 68% is dark energy, 27% is dark matter, and then roughly 5% is all the other stuff that you know about. So nuclei, neutrinos, stars, free hydrogen and helium. Okay, so this is our universe. So in the last 3 minutes or so, let me tell you, what is it? The answer, it's very easy to finish this part of the talk in 3 minutes because the answer is we do not know. Okay? It's a very simple answer. So this is an active topic of research. This is one of the things that I like to work on. Turns out that we know at least one part of the answer to this question, that it cannot be anything that we already know, which is interesting. So Professor Datar was saying that everything at the LHC has agreed with the standard model. Well, here is something that does not agree with the standard model. You know that there is mass, and you can experimentally establish that it cannot be something that you already know of. So let's just do that exercise and stop. Okay, so what is the universe made of? So let's first rule out the obvious. It is not old stars or black holes or old white dwarfs or other planets that you can't see. So you could argue that maybe it's just a whole bunch of asteroids that are not being seen. So which actually requires me to go on a little detour. I hope it's not too pedantic, but it's important. What does it mean that something is dark? What does it mean that something is dark? So let's first answer, what does it mean that I can see something? So I can see you. How? There's light that falls from, let's say, this source onto you and is reflected by you, and I sense through my eyes that reflected light. This is how I see anything. This is how a telescope sees a star. Star emits a photon, and that photon is, how does it emit a photon? Because there are protons and other things interacting within which emit a photon. So you have to have interactions with photons in order for the object to be visible. So if I have, let's say, a blob here of neutrinos, I could put a lot of mass into it. Because neutrinos do not interact with photons, I would not be able to see it. I would just be able to see through it, right? So the idea that I see something is simply a statement that that thing is composed of little particles which interact with light, with photons. So anything that doesn't do it will become invisible. Okay, neutrinos are one example. Now, but first we have to also rule out the fact that it could simply be that there is no source of light illuminating it. So suppose I have an asteroid which is not emitting its own light, just like the moon, let's say, and if you did not have the sun, you would not see the moon. But doesn't mean that it's not there. Maybe we are just miscounting. That's why we have this problem of missing mass. Point is that we can rule all of this out because very early in the universe, all of this mass would have been in the plasma, and at that point then it would have interacted. So the fact that that does not happen is our strongest argument that this missing mass all over the universe can't be made with protons, neutrons, and electrons. Case closed, right? So this makes it interesting because now suddenly I've turned the problem around. I was looking out into the universe, and now suddenly I'm talking about protons and electrons. So now, instead of looking using a telescope, I have to look using a microscope, and these two worlds have to come together. So that's practically the description of my job. I'm an astroparticle physicist. I combine observations of the universe with understanding of subatomic particles to gain better understanding of both worlds. This is extremely interesting. Let's skip a few slides. And the point is this, that you want a new particle that is stable, because dark matter has been there for 14 billion years. It has to be neutral. By neutral, I mean that it should not be electrically charged, because if it is electrically charged, it interacts with photons. That's the definition of interacting with photons. So it can't be electrically charged. It should be, at best, weakly interacting. Of course, gravitational interactions are there. And it has to be what is called cold. Cold does not just mean temperature. Cold means that it should have small velocities. It should be non-relativistic. It shouldn't be whizzing past, because then it would destroy the galaxies. So this is what is needed. And if you could find such a candidate, you are in for maybe we are in for a treat. You get to go to Stockholm. So let's see. So this is a list of known particles. This is a list of all known particles which are made of these things. So the way to read this picture is the following. There are 3 columns here. Okay? Each of these columns is called a generation. All of our known stuff is actually made of particles that are contained in this first column. Okay? So this U and D, these are quarks. They make up protons and neutrons. They are charged particles. This is the electron, and this is the neutrino that Vivek talked about. There are, of course, 2 other generations, and there are these 2 other neutrinos corresponding to these 2 other generations. The heavier electron is the muon, and this is the tau. And similarly, there are 4 more quarks. Further, there are, just like photons are the mediator of electromagnetic interactions, there are other particles that mediate other interactions, and then there's the Higgs and something that leads to gravity. Now the point is, none of these particles can be dark matter. Why? Let's first get rid of things that don't have mass, because dark matter has mass. So graviton is out of the question, photons are out of the question, and gluons are out of the question, because they don't have mass. Let's get rid of things that are not stable. Okay? These things decay. They could not have survived so long. So that leaves us just the first generation of particles and the 2 neutrinos. Okay, not so bad. But we can't have charged objects as being dark matter. So that gets rid of the up, down, and the electron. So we are only left with the 3 neutrinos. And this was the situation about 30 years ago. And people did believe that neutrinos could have been dark matter, and they could have been dark matter. If the masses of the neutrinos were a little bit higher, factor of 1,000, 10,000 larger, they could have been dark matter. But now we know that the neutrino masses are smaller than 1 electron volt. So we know that they would just whiz past us, would not lead to the kind of dark matter that we need. They're not cold, they're hot. Okay? And so that tells you there were none. Okay? So this is the situation today, that we know that there is dark matter. We know what its properties are. We know that nothing that we know of yet explains this particle. So this is a ripe opportunity for people to ask, what could this dark matter be? Okay? So I think I'll stop there. I have more slides. If you ask questions, I can go on them. But let's stop here. Point is, this is an active area of research trying to figure out what is dark matter. Right? So with that, I'll stop. I'll take any questions. Thank you, everyone.